C'est très bien. So good morning, everyone. Thank you very much for being here. It's a great pleasure today to introduce our invitee, Vincent Bourrier from the University of Geneva. Actually, Vincent did his PhD at IUP and defended in 2014. Actually, we were sharing an office at that time. So Vincent is then after the PhD, you moved for a postdoctoral position in University of Geneva, and to work on the search and characterization of atmosphere of exoplanets. Vincent is well known for his expertise on specifically the atmospheric and dynamical evolution of closing exoplanets, and Vincent received actually the Young Scientist Prize and Medal in Astrophysics from the International Union of Pure and Applied Physics. I don't remember in which year, recently. In 2019, okay. Vincent is doing countless observations and as a PI and co-I on HST, Cheops, TESS, Espresso, Narval. And Vincent got an ERC in 2021 that is called Space Dune, that I think is the topic of today's talk. So I leave you the room.
Can you hear me? Well, yes, okay. Thank you so much, Clément, for leaving and not hearing the talk. No, he warned me. Now, thank you so much for this introduction and for the organization, and to the exoplanet team also, Alain, and for inviting me, and to all of you for being here. So I'm going to try and take you with me for a trek across what is called the Neptunian desert and savannah today. So let's start with a small prologue. So I thought I would begin with this because as Clément mentioned, the last time I gave a talk here was nearly 10 years ago for my PhD defense. And so I just reported these exact figures I used at the time. Because at this time, so here you can see a representation of the galaxy with the host stars that we know are hosting exoplanets. And here you have a zoom on the solar system. And in 2014, we only knew about nearly 2,000 exoplanets, but we have kept discovering them over time. And now we are at more than 5,000. So you can still see this bunch of exoplanets that we discovered in the direction of the Kepler field. Then you can see quite more, I think, exoplanets discovered by microlensing in the direction of the galactic bulge. But otherwise, most exoplanets, we are discovering them in a bubble centered around the solar system. And these planets are the most interesting to characterize because they are orbiting a nearby star, bright stars, and so you can observe them further. Now, a more scientific way to represent this exoplanet population is like this, as a function of planet size and orbital period. So here you can see nearly all the exoplanets that we have discovered, at least those that transits. And you can see we have discovered the planets ranging from large gas giants to planets smaller than the Earth at really short orbital periods farther out. And you can see that there is some structure. Now, one of the main goals in our community is eventually to characterize in depth a planet similar to the Earth. But this remains a difficult goal to achieve because we don't know still that many planets with the size, the distance of the Earth. Hopefully the Plateau mission will discover planets like this. and it will discover planets that we can characterize, because the few Earth-sized planets that we know, they are far and they are difficult to characterize. So in the meantime, it's much easier to look at what we call close-in exoplanets. So at orbital periods below about 10, 30 days. Those planets represent about half of the known exoplanet population. They transit often, they are much hotter, so their chemistry is simpler. And so we can prepare our study of other planets by looking at those planets to develop our tools, our understanding of these planets. And so that's mainly the reason why I'm focusing on these planets. And the other reason is that if we zoom in on this close-in planet population, you can see that it's not homogeneous, right? You can see a lot of structure here. And in particular, there is a very important feature in this diagram that is called the Neptunian desert, the desert of hot Neptunes. So there is a deficit lack. There is no observational bias here. These planets were able to detect them. There is a definite lack of planets with about the size of Neptunes, but at really short orbital periods. And well, studying this desert is really interesting because it's a marker, a tracer of formation, evolutionary processes. So by looking at the desert, we can understand how these close-in planets form and evolve, what is their nature. Now, two main scenarios have been proposed to explain the desert. One scenario is atmospheric escape, evaporation, something that you know very well here. So the idea is that planets close to their stars, they got heated, they lose their atmosphere massively. And in particular, Neptunes might be sensitive enough to this process that they erode entirely. And so they go down in the previous diagram. So you are only left with a rocky core. And this process you can trace by measuring atmospheric escape, so measuring the mass lost by the planet, by observing this kind of huge tail of gas escaping from the planet. The other main scenario is orbital migration. These giant planets, we don't think they form close to the star. They form far away, and then they migrate closer to the star. But the way they migrate, when they migrate, this may depend on the type of planet. And so Neptune-size planets may migrate in a different way compared to other types of planets. So those are the two main scenarios. But we don't really know the relative roles between these two scenarios in forming the Neptunian desert. And one of the reasons we have not been able to really disentangle between the two is that we still lack measurements, so mass loss measurements for atmospheric escape and measurements of orbital architectures for orbital migration, because we expect different migrations to lead to different orbital architectures. And in particular, we expect some processes to lead to misaligned orbital architectures, like you can see here. So we still lack data to really constrain our model and disentangle these two mechanisms. And so that was the main motivation behind Spice Dune. So as Clément mentioned, this is the ERC project I obtained a few years ago. We are now at about midterm of this project. And so the goal of Spice Dune is really to understand the Neptunian desert as a way to better understand the overall evolution of close-in planets. And the way to do this, as I was suggesting, is to gather mass loss and orbital architecture measurements to then inform, develop our models of the close-in planet populations. So Spice Dune is divided into 3 work packages, one dedicated to atmospheric escape, Agathe, and the other to the coupling between dynamical and atmospheric evolution, Jade. And so today I'm mostly going to focus on these two. So let's start now with the first chapter. How do we use these orbital architecture measurements to go back into the history, the dynamical history of these planets? So here it's just to give you an idea of the various pathways that these planets can take. Okay, so you form a planetary system through the collapse of a gas cloud. You expect the system to be roughly aligned. Okay, everything is aligned within the equatorial plane of the star. Then you might get some moderate misalignments early on, either from the protoplanetary disk itself or from the star, but we expect those misalignments to be maybe about 10, 20 degrees between the disk or planets with the star. But then there are 2 main migration pathways. Either the planet migrate early on within the protoplanetary disk, and we expect this to keep the primordial alignment, okay, that was generated early on, or the planet may migrate later on through disruptive mechanisms, okay, interactions with other companions, something more chaotic, dynamically speaking. And this type of migration, as I was mentioning earlier, we expect those to really misalign completely the planetary system. And so we end up today with a variety of orbital architectures for closing exoplanets, and in particular, a variety of what we call the spin-orbit angle. So the angle between the stellar spin and the orbital normal of the planet. And this is our main observational tracer to investigate these scenarios. And so that led me to propose this program as a pathfinder to see what was possible in terms of looking at planets around the desert and better understanding their histories. So in this program, we surveyed 14 exoplanets that you can see here as blue stars around the deserts. We observed them with various spectrographs, and there were two main goals, so measuring spin orbit angles and probing the atmospheric escape of these exoplanets. In the first study, DREAM-1, we focused on the orbital architectures and dynamical histories. Okay, so again, we were interested in trying to disentangle between disk-driven migration and late migration, and to understand if Neptunes are undergoing a different evolution compared to other planets. So as I said, the way to do this is by measuring the spin orbit angle of this system. Now, traditionally, this was done by analyzing the velocimetric anomaly induced by a transiting planet. So very briefly, what we do is we look at a star with a spectrograph, and then we are able to measure the disk-integrated, so from the full disk of the star, absorption line. So this is what you see at the top. You measure the line of the star outside of the transit, and then you do the same measurements during the transit. And because when the planet is transiting, it's occulting local regions of the stellar surface, it's going to block very specific parts of the stellar surface. And this is going to induce an anomaly that you can see here as a bump in the disk-integrated line of the star. Now, if you fit your stellar line with, let's say, a Gaussian to derive a radial velocity measurement, okay, the line centroid, outside of the transit, you get the Keplerian motion of the star induced by the planets, which you can see here as a slope. But during the transit, because of this anomalous bump, you get a deviation like this. And this anomalous deviation is going to depend on the exact trajectory of the planet across the stellar disk. So by analyzing this anomaly, you can determine the spin orbit angle. Now, this is all well and good, but the issue with this technique is that you collapse all your information into a single anomalous measurement, single radial velocity measurement. So you lose a lot of signal by doing this. That motivated us a few years ago to develop a new technique that I'm going to talk in the next slide. But first, I wanted to show what it looks like for the DREAM-1 sample here. You can see the velocimetric measurements that we made for these 14 planets. For some of them, like this one here, you can see this beautiful anomaly, so it's easy to analyze, we could do it. But for many of the other systems, we don't even see the anomaly, right? It's flat, and so you get no information outside of these anomalous measurements. The planets are just too small for this typically. And so we use another technique. This technique now, it consists in taking all your measurements of the star and putting them back to the correct flux level. Because these measurements, they are done from the ground. And from the ground, because of Earth's atmosphere, you lose the absolute flux level of your measurements. And that's critical if you want to apply this technique. So we put back the measurements, especially during transit, to their correct flux level. So that's what you get at the top. And then you can do the difference between the stellar line outside of the transit and the stellar line during the transit. And if you do this, then this difference gives you just the stellar line of the region occulted by the planet. It's what you see in the middle plot. You get a series of stellar lines that are now local, just along the transit chord of the planet. And now you can analyze directly these local stellar lines. You can derive their centroids, and this time their centroids trace the radial velocity of the stellar surface along the transit chord. So it's really a direct measurement. And you can analyze this and derive the spin orbit angle again. So that's the reloaded Rossiter-McLaughlin technique that allows you already to go down to smaller signatures. But you are still limited by your ability to fit these individual stellar lines, local stellar lines in each exposure. And so it still does not work for the smallest exoplanets or the faintest stars. And that motivated us to go one step further into developing the Roster-McLaughlin revolutions technique. And now what we do is that instead of looking at individual measurements, we fit all the measurements together with a single joint model. And by doing this, we essentially boost the signal-to-noise ratio of our analysis, and we're able to go to even smaller planets or even fainter stars. And that's what we did here for the DREAM-1 sample. And now when we do this, this is what we get. So here I'm showing maps representing the local stellar lines occulted by the planets. So the x-axis is radial velocity, the y-axis is time, so time increases toward the top. And these bright streaks that you can see, this is really the absorption line of the star from the regions occulted by the planet. And now you can see that for most of the planets in the sample, we were able to detect the transit, to detect this, the absorption lines from the regions occulted by the planet. And so in the end, we were able to get 12 detections out of the 14 systems, including 6 new measurements of spin-orbit angles and 6 refined spin-orbit angles. So it was quite a success overall for this program. And this is what it looks like if you plot the orbital architectures of these systems, okay, these 12 systems. So first, it's a substantial addition to the known sample of spin-orbit angle measurements because it was still about 100. So we added, these 12 measurements. But more importantly, you can maybe see here that there is a high fraction of planets that are on highly misaligned, actually polar orbits. So the planet is going over the poles of the star, and that's a peculiar architecture. And quite interestingly, we found a much larger fraction of polar orbits in our sample. About 2/3 of the sample actually are on polar orbits, compared to the known spin-orbit angle measurements for the entire population, which is about 15%. And that's quite interesting because it indicates that there might be a specific role of this disruptive late migration, a specific role in populating the rim of the Neptunian desert. That was already quite an interesting result. But still, we were looking at only a sample focused on the desert, right? If you want to go further, you need to have a look at the entire distribution of spin-orbit angles. And in particular, you want to study the spin-orbit angle distributions as a function of various star and planet properties to be able to disentangle their role in constraining these various migrations. So several people in the community over the past years have looked into this, including Guillaume Hébrard, for example, and they proposed various trends between the spin-orbit angle and planet and star properties. And there are 3 main trends that were proposed that you can see in this diagram showing the spin-orbit angle as a function of distance, size of the planet or mass, and stellar temperature. And so here you can kind of see already that more massive planets, so larger symbols, tend to be more aligned with their star. Then planets around cooler stars, so bluer symbols, also tend to be more aligned. And maybe the most obvious trend here is that planets closer to their stars also are more aligned. So there were these trends proposed in the literature, but we wanted to go further and try to take a more global look at this. And that's a work that was carried out by Omar Atia, my PhD student. So if you are interested in this, you can go and talk with him later on. So what we did here was to reanalyze the entire distribution of known spin-orbit angles. And first, we confirmed these trends with stellar temperature, planet-to-star mass ratio, and scale distance. So, okay, that's good. We confirmed the previous trends. There is a really important word here in this sentence. It's the sky projected. Because Rossiter-McLaughlin analysis, they yield the projection of the spin-orbit angle in the plane of the sky. And what we showed in this analysis is that it's an issue because there is a strong bias toward misaligned systems. Okay, we believe systems are more misaligned than they are actually if we use the sky projected spin-orbit angle. And so we thought, okay, so what we really need now is a robust way to reconstruct the three-dimensional distribution of spin-orbit angles, so the true spin-orbit angles. And so this is the expression linking the true spin-orbit angle with the sky-projected one and the stellar inclination with respect to the line of sight. And so we build the whole framework to be able to reconstruct these three-dimensional angles. So that's one important point of the study. And the other one, as I said, is that we wanted to be able to look not at these individual parameters, but at a global parameter, because stellar temperature, mass, distance, in the end, they all relate to the tides that are raised by the planet into the star. And so we wanted, inspired by a previous study by Albrecht and collaborators, we wanted to have a global tidal efficiency factor. And well, here is the expression of this parameter. You can go into the paper for more details, but it's what we devised. And so between these two equations here, this is the result we got. So this plot here is showing the unbiased distribution of three-dimensional spin-orbit angles that we reconstructed as a function of this tidal efficiency parameter. So if you go to the right, the effect of tides is stronger. And already you can see here in this diagram an important conclusion. And especially if you look at the top, the blue bars, they represent the fraction of misaligned systems per bin of tidal efficiency. And what we found is that there is a really neat linear correlation between the fraction of misaligned systems and the tidal efficiency. That's quite useful because then we're able to fit this with a linear expression, and that gives you a first order way to estimate the probability that a system is misaligned. So you can calculate the tidal efficiency of your favorite system or maybe of your sample of system in a population synthesis, and then you can have an idea of the probability for these systems to be misaligned. And that's quite a novel approach that we think can be quite useful to the community. And then an interesting thing here in this diagram is that there are systems to the left that have such a low tidal efficiency that you can consider that their evolution was completely unaffected by tidal effects. And so you can have a closer look at these systems, which is what we did. And now here on the right, I'm showing a comparison between the distribution of three-dimensional spin-orbit angles for this pristine sample unaffected by tides and for the full distribution of the plot, so in blue. Now, there are three important points that you can get from the comparison of these two diagrams. The first point is that there is a surprising or larger than expected fraction of aligned system. And this fraction of aligned system was underestimated by previous studies looking at the sky projected angle, because as I was saying earlier, there is an observational bias in looking at the sky projected angle. So that's the first conclusion. But if you compare the pristine sample and the full sample, you can see that there are more aligned systems in the full sample. And from this, you can get that tides have a really important effect into realigning planetary systems, okay? So first conclusion. Then another interesting conclusion is that you can look at the fraction of misaligned systems, okay, in the middle of the two plots. And if you compare the pristine sample and the full sample, you can see that in the full sample, the fraction of polar orbits compared to all misaligned orbits is higher. And from this, you can suspect that polar orbits appear to be more resilient to tides than the other types of misaligned orbits. So this means that tides either prevent the formation of this orbital configuration, or they realigned later on highly misaligned systems other than polar. Quite an important conclusion also. And finally, if you look at the pristine sample alone, you can see that the fraction of highly misaligned polar orbits is actually quite large compared to the fraction of aligned orbits. And that was quite surprising. It goes against the traditional understanding that planets migrate mostly due to early on disk-driven migration that is just going to form aligned orbits. So this again suggests an important role of late disruptive migration into shaping closing planets. And into shaping, in particular, the Neptunian desert, Because again, if you look at our sample from DREAM-1, so the blue stars in the plot, you can see that they are comparatively more polar, more misaligned in their tidal efficiency range compared to the rest of the known systems. That supports again the role of these migration processes in shaping the desert. Okay, now I'm going to switch to the atmosphere part. As I said, we are interested into measuring atmospheric escape, and one good way to do this is to use helium. Now, traditionally, and this is also something that AAP has been heavily involved in over the years, traditionally, we have been using neutral hydrogen and ultraviolet observations to probe atmospheric escape. So essentially, if you want to probe the atmosphere of an exoplanet, what you do is that you look at the transit in different wavelength bands. And if the planet has some structure, different species, you expect to see different absorption depths at different wavelengths. So this is what you do. You go from this transit here to this transmission spectrum showing the absorption from the atmosphere at different wavelengths that is going to trace the presence of different species in the atmosphere of the planet. Hydrogen, neutral hydrogen, is a really great probe of exosphere, so of really the huge tail of gas once it has escaped from the planet. But it has a few issues, a few limitations. It's strongly absorbed by the interstellar medium, so that limits your ability to probe exoplanetary systems to nearby systems. There is not a bright stellar continuum in the far UV, so that's also an issue to do transit spectroscopy. You need bright stars. And finally, you need the Hubble Space Telescope to do this kind of observations at high resolution. So over the years, we could not observe a lot of systems in the end to search for neutral hydrogen escaping from exoplanets. But recently, helium was kind of rediscovered as a great probe of atmospheric escape. Because with helium, you can probe both the thermosphere and the exosphere of exoplanets, so all the upper layers that expand and escape because of the heating. Helium is not absorbed by the interstellar medium, not for a really long distance. And, well, it's in the near infrared, so there is a really bright stellar continuum. And you can observe it from the ground as well as from space. And from the ground, that's great, because then you can use all the high-resolution spectrographs that are being developed. And here I'm showing you one of the very first measurements that we obtained. So this is kind of still under embargo, so please no pictures. It's a recent measurement obtained with the NIRPS spectrograph that just started its operation recently. And this is really a beautiful detection of a helium absorption signature here at the top, average over the transit. Below, I'm showing a map, okay, so wavelength and time, so a map of this absorption over time. You can see it's well within the transit, detected in all exposures. And here it's a light curve, so you just integrate within the band of helium the absorption, and you can see the evolution of the signal. And one interesting point from this light curve is that it's not symmetrical, right? You can see that there is some post-transit absorption in particular that is tracing the presence of a tail of helium trailing the planet. So we are really probing here the gas escaping from the planet, just to illustrate the potential of this helium probe. Now, as part of DREAM, as I was saying earlier, we also wanted to probe atmospheric escape. And DREAM, we observed those planets with both optical and near-infrared spectrograph, the near-infrared spectrograph JANO. And so we wanted to do the same kind of studies as I just showed before with NIRPS. But JANO is not exactly quite like NIRPS in terms of sensitivity in particular. And so to the right here, I'm showing the equivalent plots that I was showing previously. And well, you can see that we didn't get in the end any detection out of the sample. So our sample from DREAM-1 was those pink targets. So no detection whatsoever, which was, I mean, okay, partly due to the sensitivity of NIRPS, but it was also a bit surprising. Because it was surprising to not detect anything, it brought some constraints on why don't we observe anything? You know, why the stellar and planetary properties of our system do not populate this helium absorption. So in the end, we combine our sample with another sample from Allard et al. 2023, so the blue points in the diagram, because we made together the same reduction, same analysis, so we are able to compare our results. And what we did was to, so our sample here are the blue measurements, the sample from, the black ones. And the blue measurements are from Allard et al. 2023. So we took our measurements and we set some upper limits on the absorption from helium at the top, the scale height of the planetary atmosphere, and the mass loss at the bottom, derived by fitting those atmospheric signature or non-detection with one-dimensional atmospheric models. So in the end, we put some constraints out of our measurements. We seem to support some correlation previously proposed in the literature between the presence of helium absorption and either the stellar mass or the XUV irradiation. There seems to be in this, it's difficult to see, but there is a range here toward the middle of the plot that seems to be more favorable to populate the helium lines. And this corresponds roughly to K-type stars. So we kind of support these conclusions. But then when this is true for the absorption and the scale height, not so much for the mass loss. The mass loss, we are not able to get much out of it, no strong correlation whatsoever. And so, well, we took two conclusions out of this study. The first is the importance of doing homogeneous global analysis of large sample like this, if we want to really understand the potential of the helium probe to get information out of it. And the other is that, well, you cannot just use simple one-dimensional model if you want to properly estimate the mass loss out of these measurements. I'm going to go back soon to this point. But so these results also motivated us to go larger, to go broader. Okay, we need a lot of measurements of helium if we want to understand what's happening with this probe and to understand atmospheric escape as a whole. And so in Geneva, right now, we are developing a new instrument, a new spectrograph to target specifically the helium probe. So this project is led on the engineering part by Casper Faret-Jenkin, a PhD student in Geneva. And the idea is to develop, NIGHT, the spectrograph, which is a compact, you can see the size here compared to a human being. It's really small. So a compact, low budget, but high resolution near-infrared spectrograph. It's a really, really high resolution. It's actually comparable to existing larger spectrograph. But we are just focusing on a narrow spectral range that you can see here in the simulation of what we will observe, hopefully. So to the left, you can see an image of the detector of the instrument, and we are just really going to observe a small narrow band around helium. And that makes it much easier to develop and to, well, fund also the instrument. And in the end, we hope to be able to observe this kind of typical signature, absorption signature from helium, but in really large sample. You have here a preliminary sample of what we hope to observe. So the interest of NIGHT is really that since it's going to be dedicated to helium, we are just going to survey, to monitor all the time transits of exoplanets and accumulate measurements of helium absorption and also search for temporal variability, hopefully, in the atmospheric escape. We are aiming for a first light toward the end of next year, maybe 2025, but it should come hopefully quite soon. But okay, so what are we going to do with all these measurements, right, of helium? How are we going to interpret them in terms of mass loss? So that's where the model come in. As I was mentioning earlier on, we derived some constraint out of the helium measurement by using simple one-dimensional models. Models like the P-wind code, which are based on a Parker wind approximation that deal with simple hydrogen-helium chemistry and that do simple radiative transfer. So essentially, you calculate your density profile of hydrogen, your velocity profile, and then you calculate on top of this the specific chemistry of your helium in the near infrared. And then you fit, so this is again the absorption signature from NIRPS fitted with this model. Well, you can get this nice red fit and get a mass loss out of it. But if you look closely here, you can see this wave in the transition spectrum. And this is induced actually by the Rossiter-McLaughlin effect that I was mentioning earlier in the seminar. And this is typically a three-dimensional effect, right, due to the transit chord, disorientation, etc. And so it's an indication that you should be cautious about using simple one-dimensional models that do not account for this when fitting this kind of observations. And so that's our main motivation to use a code that started from work here, actually, so the Eve code. So Eve, it's mainly a three-dimensional framework into you simulate an exoplanet system with a stellar surface that is spatially and spectrally resolved. So you can put whatever stellar spectrum you want in this stellar grid. And then you have the planet transiting in 3D with a thermosphere. And in this thermosphere, you can put whatever structure you want. So here we just put this one-dimensional vertical structure from Pwind, but since the code is itself three-dimensional, you already can get further into probing geometrical effect and the impact of the stellar surface. And so this simulation was performed by one of my PhD students, Yann Carteret, specifically for the NIRPS system, as I was showing earlier. And you can see that we are producing the helium signature from the thermosphere of the planet, but we are also naturally reproducing this Rossiter-McLaughlin distortion, thanks to this kind of code. So that's great. We can go one step further into interpreting these observations. But if you remember, I was mentioning earlier that the NIRPS observation shows an asymmetrical light curve, right, with a post-transit absorption. And here, if you have just a spherical thermosphere, you are not going to reproduce this. You just get a symmetrical light curve. And so you can go even one step further and use the exosphere part of Eve. So on top of your thermosphere, you are letting helium atoms escape and form naturally this comet-like tail. And you can see here in the simulation that you not only get the contribution in terms of absorption from the thermosphere, but also, you're going to see it again, you get a contribution, an asymmetrical absorption signature from the exospheric tail of helium going to the blue. And so it's just a preliminary fit. It's just dating 2 weeks back, so it's not a fit yet. But you can see already with the red light curve that now we are producing something that is asymmetrical and reproducing post-transit absorption. So we are going to fit this study, informed by results also of the Rossiter-McLaughlin analysis of the system. And we hope to get in the end a really accurate mass loss measurements out of these observations. And what we will do in the end with all these spin orbit angle measurements and mass loss measurements. That's the last part of the seminar. So just to sum up, we have seen that this driven migration happening early on is probably not the dominant process for all closing planets. Okay, we believe that high eccentricity migration is going to shape differently the evolution of some of these planets, in particular by delaying the evaporation of some of these warm Neptune. And so what we need is to use these mass loss and orbital architecture measurements to inform dedicated, detailed models of this type of evolution. And that's another big part of the work that has been carried out by Omar during his PhD, developing such a model. So we developed the JADE code, which is a three-dimensional dynamical and atmospheric evolutionary code. Okay, so we go from the top, where you are just after the formation of a planetary system with your star, an inner planet, but formed at a certain distance, and then possibly an outer companion. And then you simulate the dynamical evolution of this planet due to the tides raising the star, due to the influence of the outer companion. But compared to what has been done in the past in the literature, now you just don't simulate separately the atmospheric evolution and the dynamical evolution of the planet. You simulate the two together with really high temporal and physical, let's say, precision. And you end up with your planet that evolves over time in terms of atmospheric structure, in terms of mass loss, and in terms of orbital properties due to the migration. Again, you can go and talk with Omar or have a look at his paper to better see all the physics that went into developing this code. Just to illustrate, so we applied the code to a flagship target, let's say, a really prototypical warm Neptune that is called GJ436b. So it's a really interesting system that has been studied a lot over the years because the planet is on an eccentric orbit, but it's close to the star and it's old. It's like 6-8 gigayears. So we would have expected it, if it had migrated early on, to have been circularized by the star due to tides. But it's not, right? It's an eccentric orbit. And then we found that it's on a highly misaligned, actually polar orbit. And as we saw, this is indicative of a disruptive, probably, migration. And finally, the planet is strongly evaporating. And that's also a bit surprising because over 8 gigayears of strong evaporation, you would have expected the planet to erode much more than this. So in the end, how did it survive, right, at the inner edge of the deserts? Probably, we believe, because it underwent a late, delayed migration. So to explore this scenario, we informed Jade with the measurement of this polar orbit, with the measurement of the mass loss rate from the planet, and we simulated the evolution, and those are the results. You can see here the temporal evolution of the eccentricity of the orbit, the semi-major axis, so distance to the star, the three-dimensional spin-orbit angle, and the mass of the planetary envelope, with the planet not at its right position. Sorry about that. But so the important point here is that there are two phases. There is a first phase when the planet has formed, is far from the star, and it gets trapped into a resonance, dynamical resonance with an outer massive companion. And so for about 5 gigayears, the planet remains trapped far from the star, so safe from evaporation. And then at some point, it goes out of the resonance. It migrates very fast towards the star, but the eccentricity does not, the eccentric orbit does not circularize that fast. And so that explains why the orbit is still eccentric today. The planet, this mechanism of resonance is an exchange between the eccentricity of the orbit and the inclination. And so this mechanism naturally explains highly misaligned orbits. And that's what we were able to simulate here, an orbit that is naturally misaligned polar today. And finally, because the planet migrated later on, it only started evaporating massively when it migrated. And so that explains also its survival at the inner edge of the desert. So this really illustrates what we intend to do later on with a larger sample of closing exoplanets, to apply these kind of simulations and in the end be able to disentangle between Neptunes that had a smooth early on evolution and Neptunes that underwent this kind of evolution. And so that will be the epilogue of this talk. But actually, if you remember, the title of the talk was the Neptunian desert and savannah, right? And I mostly talked here about just the deserts. So let's just have a word about the savannah. If you look at this plot, now the savannah is this region here at longer orbital periods. The desert, it's a definite lack of Neptune-size planets. There are no Neptunes, so probably they're all eroded or, well. But in the savannah, you have more Neptunes, but still not that many Neptunes, okay? And over time in the literature, people have been assuming that this is due to a formation mechanism. Neptunes are harder to form because as soon as a rocky core is able to accrete gas, it's going to go directly to Jupiter size. So it's harder to stop at Neptunes. But well, I thought, okay, this is happening maybe, but this is happening beyond the ice line where the Neptunes are forming. So maybe, okay, this explains the lack of Neptunes beyond the ice line, but here we are not beyond the ice line, we are much closer. And so, is this distribution here of Neptunes really tracing exactly what's happening beyond the ice line? Or is the migration of Neptunes changing the view? Does it have an influence here? And so that motivated us to propose a large program on the VLT Espresso at Radis, to build this distribution of spin orbit angles for the Neptunian population. So all the diamonds here are the targets we are going to observe over the coming 2 years to measure their spin orbit angles. So it's a huge investment of ISO, of us also, of all the collaborators in this program, because it represents 60 planets transiting. So it's with about 60 collaborators as well. So it's really a mini GTO. And my PhD student, Michel, is also helping a lot with the organization of this program. And it's a huge collaboration also with the NGTS photometric survey, who are helping us revise the ephemeridis of these planets. So stay tuned if you are interested in the coming years for results about the program. The first observation actually was 3 nights ago, and I'm quite happy to show it. It's here. You have this very beautiful Rossiter-McLaughlin anomaly. So this is just a preliminary reduction, but that was made like just in the morning by the observer of the night. She did a really fast analysis. And here you can see it's an aligned system. And it's the first time we measure the orientation for this system. So we are quite happy about this measurement. The precision is incredible. Thanks to Espresso and the VLT. So that's what I hope to see for, well, most of the planet in the sample. And I think it's nearly time, so I will just leave you with a few perspectives on Spice June for the second part of the project. On the atmospheric part, we hope to go a bit further into the description of the thermosphere. So my PhD student, Jan, who I mentioned earlier, is developing a two-dimensional model of the thermosphere to better interpret helium absorption. Then we also, in the third work package, looking at those rocky body at the lower border of the desert, because some of those might be the remnant cores of evaporated Neptunes. So I'm really interested in trying to make the link between evaporating Neptunes and maybe those rocky cores. And finally, in terms of coupling the dynamical and atmospheric evolution, we want to go, as I was mentioning, broader and to implement the kind of simulations we are doing with Jade into population synthesis to be able to really try and simulate the entire population of closing exoplanets. And I will leave you now with these few last messages. Thanks.
Thank you very much. There's a lot of work. Do you have questions?
Thank you. If I may start all the questions, I didn't notice the telescope on which the night spectrograph should be mounted. Maybe I missed the information, but
No, you didn't.
But it's a secret.
No, it's not a secret, but you didn't miss it because I purposely did not mention it. The reason is that we don't know yet. So we designed a night by starting with science requirements, okay, which was our ability to detect temporal variability in helium absorption between two transits at a certain level. And we said, okay, we want to be able to detect this on a 2-meter class telescope. So our requirement is that we want to install it on a 2-meter class telescope, but it was not necessary to decide early on which telescope. There are actually a lot of 2-meter class telescopes in the world that we can ask to be installed on. No, but actually, yes, there are a fair number of them. So we have a few leads. One of them, for example, is OMM, so on the Mont Mégantic in Canada. That's a possibility. There are telescopes in La Palma or in Chile. We are actually thinking about this right now, literally trying to discuss collaborations to install it. So we are developing NIGHT as a visitor instrument so that it's really easy to plug in and to unplug and to change. So maybe we'll like change telescopes every, I don't know, 3 years, 4 years, you know, to change latitude, also maybe observe a different part of the sky. Pretty the idea.
Other questions?
I know you already spoke about this, but I'm wondering if you could just explain it again, why you detected so many polar orbits and why there was the difference between this pristine sample and the wider sample in terms of the polar orbits in particular. Because in my mind, I see planet formation happening in a disk, and that disk is more aligned with the star. So how does it then kick into this polar orbit, and why is it so prevalent? Thank you.
Okay, I mean, okay. There are a lot of answers to your question, a lot of things to say about your question. But so, I mean, how it happens exactly, it's dynamical interactions most of the time between companions. It can be stars, it can be other planets, and the inner planet. So the scenario we are mostly interested in is quasi migration, so quasi lead-off cycles. So as I showed with Jade, you really have an exchange of between the eccentricity of the planet and the inclination. Okay, so it's 3 cycles where the eccentricity changes and the inclination changes, and so that's how you misalign really highly your planetary system later on. There are other mechanisms like scattering, for example, with other planets. But so it's what we put into the general umbrella of high eccentricity migration mechanisms. Okay, so that's how you form polar orbits. Then, I mean, why specifically at the border of the desert? I would say that it's still what we are investigating, right? I mean, I'm not completely sure exactly why. I have a feeling, an intuition, we'll see if it's true, that high eccentricity migration might specifically populate the border of the desert. So that the planets, a large fraction of the planets we find at the border of the desert underwent this high eccentricity migration, and that's why they end up polar. I don't know why it would be different. It appears to be different within the savannah. With the savannah, planets, from what we can see, seems to be more aligned. So I don't know, maybe the planets are migrating directly into the border of the desert, after they go out of quasi migration. That's something we will investigate. I'm not sure exactly why, what's happening, but that's really the purpose of the program, to do this.
How many M stars do you have in your sample? Probably you're in the visible, so not many.
For night, you mean, or for...
in a different target you're observing, how many M dwarf do you have?
M dwarf. In this, you mean?
Yes, if I know. Among the 60.
Yeah, I don't think indeed there are that many M dwarfs because it's optical and espresso, so I don't think we have a lot. In the end, we'll try to see if there are differences, of course, with stellar type, because there is a strong influence of tides with stellar type. No, it's mostly G and K-type stars, I think, in the end here.
Other questions?
Sorry, but if I may, to me, this is also complemented by the work we are doing with NIRPs. And with NIRPs, we are mostly targeting M dwarfs, obviously. So, yeah.
Other questions?
So for the planet with the quasi mechanism, you say that basically it started to evaporate when the semi-major axis decreased. But I was wondering, when the planet is at its pericenter, does it evaporate or is it too fast?
Yes. So that's naturally included in the code. Okay, we kind of integrate the mass loss over the orbit. So if the orbit is more or less eccentric, it's going to change the evaporation in the code. But then, I mean, probably, but there have been also studies of how an atmosphere reacts to fast changes in irradiation. That was done mostly for flares, I think, but also I think for one study for this kind of problematic close to the peristron. And if I remember correctly, the conclusion was that the atmosphere does not react that fast to changes in irradiation. To reach a completely different state regime, you need to have some long time for the atmosphere to kind of stabilize. So yeah. I think the passage at peristron is quite fast in general, and I'm not sure the planet reacts that fast, and is losing so much more mass because of this passage.
Actually, I have a quick question about population synthesis model. So the work you will do, you said you will do. I was wondering how will it be included in the synthesis model done, for example, by Mordassini? I'm not sure I have a clear idea. Is it complementary? And
yeah, okay. I cannot say I have also completely a clear idea yet. So it's interesting that you mentioned Christophe Mordassini, because we will supervise together a thesis to re-carry out this project. So quasi lead-off migration is really not easy to simplify into just analytical formulas. That's why we developed J, to be able to do this kind of simulations. So the way I see it, there are two possibilities. Either we will be able to find some approximate analytical formula to describe the evolution or the timescales of quasi migration. That's something Omar has started to investigate. I think we have good prospects of being able to find something like this. Then you can implement it into the population synthesis to say, okay, this is going to happen for this planet now, etc. The other possibility, maybe we are going to do the two probably, is to generate a grid of simulation. This is the kind of thing that has been done for atmospheric escape. People have been generating a lot of evolutionary grids, okay, depending on a few key parameters. And then you go, for a given system in the population synthesis, you go and you interpolate essentially your evolutionary grid. So I think we'll do something like this with Jade. We'll generate grids to be available actually to the community and also beyond our work with the population synthesis, and then we'll go and retrieve them and use them.
Okay. I just mentioned if people in remote want to ask questions, they can.
Vincent, what would happen exactly to this picture if there were not the mechanism that you're talking about? Would that be void, or would that be more filled?
Okay, that's a good question. I would say that if there was not high eccentricity migration, the desert would be more empty. I would say that planets, if they migrated, all of them migrated early on, then those planets that migrated early on would have evaporated straight away, eroded, and so they would be below the desert. My suspicion is that a substantial fraction, I don't know how much, but a substantial fraction of these close-in Neptunes, they are there, still visible today, because they migrated recently due to high eccentricity migration, and so they did not have the time to evaporate strongly. I think that's how it would change, mostly the picture.
Is it true also in the savannah? It would be.
This I don't know, because it's not clear right now still how far into the savannah evaporation is an active, strong mechanism. There was a study years ago that was made for hot Jupiters, giving, I think, 11 days, something like this, as a limit for a planet to lose its stability and enter the hydrodynamical escape regime. But that was one study, and it was made for hot Jupiters. So for hot Neptune, I don't think it has been explored that much. So that's also something we'll investigate with helium and with other measurements.
Okay, I don't see questions in remote. Maybe a last one. This is your last chance. Okay.
Well,
so anyway, yeah, so Vincent Bourrier will be around all day long. If you want to chat with him, he will be at the mezzanine probably. It will be also an opportunity to explore the mezzanine for the newest. It's a totally normal part of IAP, trust me. Also, if you want to have lunch, if you are interested, particularly to speak with Vincent, please come and ask. Thank you again, Vincent.
Thank you to all of you.